Nobody told you the universe was supposed to make sense. That's the first thing I want you to understand. Not because it doesn't make sense, it does. It fits together with a coherence so deep and so precise that it will make you cry if you stare at it long enough. But because the part of it that makes sense is the small part, the manageable part, the part we've had long enough to domesticate. What NASA keeps running into, what keeps getting quietly filed under anomalous results pending further investigation, is the part that doesn't domesticate. And I want to talk about that part tonight. Not because I enjoy confusion. I hate confusion. I have spent 50 years trying to eliminate it, one equation at a time. But because this particular kind of confusion is not failure, it's invitation. And we keep RSVPing maybe next year. Let me start with something that will sound like it can't possibly be true. The universe is expanding faster than it should be. Not a little faster, not within the margin of experimental error, faster in a way that has now been confirmed by 6 independent measurement techniques using completely different physical phenomena: Cepheid variable stars, gravitational lensing, baryon acoustic oscillations, the cosmic microwave background, type Ia supernovae, and surface brightness fluctuations in distant galaxies. All of them. And they don't agree with each other. They disagree by approximately 9%, which in cosmology is not a rounding error. In cosmology, 9% is a chasm. It's the difference between a theory that works and a theory that is wrong. And right now, one of our foundational theories about the structure and history of the universe is almost certainly wrong. We do not know which one. This is called the Hubble tension, and if you have not heard about it, that is not an accident. It tends to get buried under more photogenic announcements. But the people who work on it, and I want to be clear about this, are not a fringe group. They are some of the most careful, most rigorous observational cosmologists alive. Wendy Friedman at the University of Chicago, Adam Rees at Johns Hopkins, the entire Planck collaboration in Europe. These are not people who are sloppy. When they report a 9% discrepancy and say they cannot explain it, they mean they genuinely cannot explain it. They have tried. They have checked for systematic errors, instrument calibration problems, unmodeled dust absorption, selection biases. They have triple checked, and the discrepancy remains, and it has been getting more statistically significant with every new data set, not less. So what is going on? The honest answer is we don't know. What we can say is this. When we measure the Hubble constant, the rate at which the universe is expanding right now, using local measurements of nearby galaxies, we get one number. When we infer what the Hubble constant must have been from the cosmic microwave background, the afterglow of the Big Bang, and then project forward to today using our best model of how the universe evolves, we get a different number. The model that connects those two measurements is called the lambda CDM model, and it is the standard model of cosmology. It has been our most successful large-scale framework for 30 years. And it is either incomplete, or it contains something wrong, or there is new physics operating between those two measurement epochs that we have not yet identified. Those are the options. There is no comfortable option among them. You're probably sitting there thinking, maybe it's just a measurement error. Maybe one of those 6 methods has a subtle flaw. And that's a reasonable thing to think. But here is why the tension is serious. 2 completely different communities, one studying the early universe, one studying the local universe, using completely different instruments, completely different physical processes, completely different mathematical machinery, keep getting these 2 inconsistent numbers. The chance that both communities have made independent correlated errors that are consistent within themselves but inconsistent with each other is not 0, but it is not large. And as the error bars have shrunk with better data, the tension has not resolved. It has sharpened. When your discrepancy gets more significant as your measurement precision improves, that is the universe telling you something, and what it is telling you may be among the most important things it has ever said. Now, here is where it gets strange. One of the candidates for what's missing from our model is called early dark energy. The idea is that there might have been a brief episode of accelerated expansion in the early universe before the microwave background was formed that we have not accounted for. Another candidate is a modification to the equation of state of dark energy itself. The possibility that the thing we call dark energy is not a cosmological constant, not a fixed property of empty space, but something that changes with time, something dynamic. Another candidate, and this one I find genuinely unsettling, is that the universe is not as smooth on large scales as our model assumes. There may be a large scale flow, a bulk motion of matter across a region of space so vast that we have been sampling it from the inside without realizing it, and that local motion is contaminating our measurements of the cosmic expansion rate. None of these explanations is clearly right. All of them have problems. All of them change what we think the universe is made of, or how it behaves, or both. And this is the case where we don't even have a solid anomaly to grab onto, just an inconsistency between two numbers. Wait until I tell you about the cases where we have hard data we cannot explain at all. I want to tell you about the flyby anomaly. This one has a different flavor, and it has never been satisfactorily resolved, and most people outside of mission navigation teams have never heard of it. Here is the situation. When a spacecraft needs to pick up speed without burning fuel, it performs a maneuver called a gravity assist. The spacecraft swings around a planet, uses the planet's gravity and orbital momentum to accelerate, and flies off faster than it came in. This is not exotic. We have done it dozens of times. It is how Voyager 1 got to the outer solar system. It is how the New Horizons mission reached Pluto. It is standard orbital mechanics, well understood, calculable to extraordinary precision, except that several times, when spacecraft have performed gravity assists past Earth specifically, they came out moving faster than our calculations said they should. Not much faster. We are talking about anomalous velocity changes on the order of millimeters per second, fractions of millimeters per second in some cases, but our trajectory calculations for these spacecraft are precise to better than that. We model every known force. We account for solar radiation pressure, general relativistic corrections, atmospheric drag at altitude, the gravitational influence of the moon, the oblateness of Earth's rotation, all of it. And still, sometimes, the spacecraft emerges from the flyby, moving at a speed that is not exactly what the equations predicted. Sometimes faster, once, apparently, slightly slower. The phenomenon was named by John Anderson, a JPL physicist who was analyzing the Galileo flyby of Earth in 1990. He found a small but statistically significant discrepancy. He checked everything. He published a careful paper. Then it happened again with the Near spacecraft in 1998, again with Rosetta in 2005, again with Messenger. There appeared to be a pattern. The magnitude and sign of the anomaly seemed to correlate with the entry and exit declination of the spacecraft relative to Earth's equator, which suggested something geometric, something connected to Earth's rotation or its gravitational field at different latitudes. Several theoretical papers were written proposing explanations. Dark matter concentrated near Earth, a modification of inertia at very low accelerations, an unexpected coupling between the spacecraft's velocity and Earth's frame dragging effect from general relativity. None of them have worked cleanly. More recent flybys, Rosetta's subsequent passes, the Juno flyby of 2013, showed little or no anomaly, which has made the problem harder to characterize rather than easier. Either the effect is real and erratic, or it is real and we have since corrected some unidentified systematic error in our models without realizing it, or it was never real, and we were fooled by a combination of subtle instrumental effects that happened to have fooled us consistently in one direction. I genuinely do not know which of those is the right answer. Neither does anyone at JPL. Neither does anyone anywhere, as far as I can tell. What troubles me about the flyby anomaly is not the size of the effect. It's tiny. What troubles me is the geometry. If the anomaly correlates with the spacecraft's entry and exit trajectory relative to Earth's rotation axis, that is not nothing. That is a structure. And structures have sources. If you see a pattern in the residuals of your best physical model, the pattern is telling you something about physics that the model is missing. We do not know what that something is. And because the effect is small and the flybys are infrequent and expensive to instrument properly, we have not made it a priority to find out. That, I think, is a mistake. Now let me tell you about something that cannot be explained as a subtle calibration error. Something that arrives from across the universe and punches you in the detector with the energy of a fast-pitch baseball, except that fast-pitch baseball is a single particle, an elementary particle, a single proton or atomic nucleus. In 1991, a detector in Utah called the Fly's Eye detected a cosmic ray with an energy of approximately 3 times 10 to the 20th electron volts. This has been called the "oh my God" particle, which is not a scientific name, but is a viscerally accurate description of what it was like to see it in the data. The problem with this particle, and this is where you need to stay with me, because the physics here is genuinely extraordinary, is that it should not exist. Let me explain exactly why. The universe is filled with the cosmic microwave background radiation, the same ancient light from the Big Bang that I mentioned earlier. These photons permeate all of space at very low energies, roughly corresponding to a temperature of 2.7 Kelvin, just barely above absolute zero. For most purposes, cosmic ray particles moving through the universe interact with this background radiation only rarely, and the interaction is negligible. But at sufficiently high energies, above roughly 5 times 10 to the 19th electron volts, which is called the Greisen-Zatsepin-Kuzmin limit, or the GZK limit, something changes. At those energies, the cosmic ray particle is moving fast enough that in its reference frame, those CMB photons are not low-energy microwave photons anymore. They are gamma rays. And when a proton collides with a gamma ray, it undergoes a reaction that produces pions and sheds energy rapidly. The mean free path, the typical distance a proton can travel before losing most of its energy through this process above the GZK limit, is only about 50 to 200 megaparsecs, roughly 160 to 650 million light years, cosmically speaking, nearby. Next door, almost. The oh my God particle and dozens of similar ultra-high energy events detected since have energies above the GZK limit, which means they cannot have come from more than a few 100 million light years away. That seems like it might make them easier to explain local sources, except that when you look in the direction those cosmic rays came from, accounting for the deflection caused by magnetic fields, there is nothing there obvious enough to explain them. The sources of the most energetic particles in the observable universe are among the most poorly understood objects in the observable universe. The leading candidates are active galactic nuclei, the engines of quasars, regions around supermassive black holes where matter falls in, and magnetic field lines accelerate particles to extraordinary energies and gamma ray bursts, the catastrophic death cries of massive stars. But the correlations between ultra-high energy cosmic ray arrival directions and known sources remain weak. The acceleration mechanism that produces these particles, if it is a single mechanism, has not been definitively established. This matters beyond the academic. The most energetic physical process we know of in the universe is happening somewhere, regularly, and we cannot locate it with confidence or explain the physics of how it works. The particles are real. The detectors, Auger in Argentina, the telescope array in Utah, see them. They are not a ghost in the data. They are the most energetic individual objects we have ever detected, and their origin is murky. I should tell you about something I found wrong in my own thinking around this area of physics. For a long time, I was comfortable assuming that the GZK cutoff would act as a clean ceiling in the cosmic ray energy spectrum, that above the limit, you simply would not see many events, because sources were far and the propagation penalty was severe. The Auger data accumulated over the last 2 decades shows that the spectrum does seem to soften above the GZK limit, which is encouraging. But the most extreme events are still there, still arriving, and the anisotropy, the clustering of arrival directions that would point us firmly towards specific source classes, has been tantalizingly weak. I expected the sources to announce themselves more clearly once we had enough events. They have not. And I have had to sit with the possibility that the magnetic field structure of the universe between here and those sources is complicated enough and poorly enough understood that we are doing source astronomy through a funhouse mirror. Now, here is where it gets genuinely strange. In 1977, a radio telescope at Ohio State University, part of the SETI program, detected a signal. Jerry Eman, a volunteer astronomer reviewing paper printouts of the data, circled the signal and wrote in red pen in the margin. Wow! The signal lasted 72 seconds, exactly as long as a signal from a fixed point in the sky would be expected to last as Earth's rotation swept the telescope's beam past it. It was at the hydrogen line frequency, 21 centimeters, which is the frequency SETI had long identified as the most physically motivated place to look for an intentional signal from a technologically capable civilization. It was narrowband, far narrower than any known natural emission process produces. It was approximately 30 times stronger than the ambient background noise. It had the spectral shape expected of a point source. It has never been detected again, despite repeated searches pointed at the same region of sky with more sensitive equipment. I want to be precise about what I am and am not saying here. I am not saying the wow signal was a transmission from an alien civilization. I have no evidence for that claim. What I am saying is that we do not have a natural astrophysical explanation for it that is widely accepted. The proposals that have been made, comets outgassing hydrogen, reflecting sunlight, have serious problems. The two comets that were retroactively identified as being near that part of the sky in 1977 were not where they needed to be for the geometry to work, and the hydrogen emission from solar system objects is not narrow enough. The signal remains unexplained. A single data point is not evidence of anything by itself. But a single unexplained data point at the frequency and bandwidth and strength and duration of what an intentional signal would look like, pointing from a specific region of sky with no natural explanation on offer, that is a thing you should not forget about. That is a thing you should find at least as interesting as whatever you were going to read on the internet tonight instead of thinking about it. Let me connect this to something broader. One of the deepest scientific questions I have ever sat with is the question of what the silence of the sky means. Enrico Fermi, at lunch in Los Alamos in 1950, asked a question that has gotten worse every decade since. If there are other technological civilizations out there, where are they? The galaxy is 400 billion stars. It is 10 billion years old. Even at modest fractions of the speed of light, a civilization that started expanding 1 billion years ago could have colonized every star system in the Milky Way multiple times over by now. They are not here. Their transmissions are not obviously visible. Their engineering projects on stellar or galactic scales are not obvious to us. Why not? This is called the Fermi paradox, and I want to tell you why it is not a trivial question. The space of possible explanations is large. Perhaps life is extraordinarily rare, arising only once or a handful of times in a galaxy's history. Perhaps intelligence is extraordinarily rare even given life. Perhaps technological civilizations reliably destroy themselves before they can expand, which, given what I have observed of our own civilization, is not a negligible hypothesis. Perhaps they are here and we have not recognized them. Perhaps the nature of advanced intelligence leads inevitably to some form that does not make the kinds of signals we are looking for. Perhaps communication across interstellar distances is simply not attempted for reasons we do not yet understand. Perhaps we are in a galaxy that has been colonized and structured in ways that are invisible to our current instruments. Every one of these possibilities, if true, has enormous implications for what we are, what we might become, and how we should think about our future. The silence of the sky is a scientific data point. We have collected it now for 60-some years of increasingly sensitive radio astronomy, and more recently, optical SETI. And the result is a null result that is itself evidence. It is evidence for something. We are arguing about what? But do not let anyone tell you this is a philosophical question rather than a scientific one. It is a scientific question. The universe has an answer to it. We do not know the answer. There is something closer to home that NASA has been grappling with that has a different but no less profound flavor. It involves a gas called phosphine and a planet we used to think we understood. In September of 2020, a team led by Jane Greaves at Cardiff University announced the detection of phosphine in the atmosphere of Venus at altitudes of around 50 kilometers, where temperatures and pressures are roughly Earth-like, far above the hellish surface. Phosphine, pH3, is a molecule that is produced on Earth by certain anaerobic bacteria and by industrial chemical processes. In the context of planetary atmospheres, its presence is considered a potential biosignature, not because it is impossible to produce abiotically, but because the abiotic processes that could produce it in a planetary atmosphere require very specific conditions, and the quantities detected in Venus's atmosphere, roughly 20 parts per billion, were substantially larger than known abiotic processes in Venus's environment could easily account for. The paper triggered an immediate and intense scientific response. People reanalyzed the data. There were questions about spectral calibration, about interference from sulfur dioxide absorption. The original team revisited their analysis and found that the initial estimate had been too high. The phosphine abundance was smaller than first reported, perhaps 5 to 7 parts per billion rather than 20. But even at that lower abundance, the abiotic explanations remain strained. Lightning chemistry can produce phosphine, but not at the concentrations needed. Volcanic outgassing can contribute, but the geological activity required would itself be anomalous. The question of whether Venus's atmosphere contains more phosphine than chemistry alone can easily explain is genuinely open. And if it does contain anomalous phosphine, the biological explanation, while not established, while not even the favored hypothesis of most planetary scientists, has not been ruled out. I'm telling you this not to suggest that there are bacteria floating in the Venusian clouds, though I confess that the image delights me in a way I cannot suppress entirely. I am telling you because the philosophy here matters. We detected something we could not immediately explain in the atmosphere of our nearest planetary neighbor. The correct scientific response is not to immediately reach for the most dramatic explanation, and it is also not to immediately dismiss it. The correct scientific response is to design better observations, send better instruments, get better data. We have not done that. Venus has been remarkably underexplored relative to Mars. The reasons are partly technical. The surface environment is crushingly hostile, but the cloud layer, where temperatures are hospitable, is achievable with current balloon technology. We have not prioritized it. We should. Here is something else we do not understand, and this one touches on some of the deepest physics I know. When the Voyager 1 and Voyager 2 spacecraft crossed the heliopause, the boundary where the solar wind terminates and the interstellar medium begins, they found things in the structure of that boundary that our models did not predict. The heliosphere is not the simple bubble our model suggested. The interaction between the solar wind and the interstellar medium is more turbulent, more asymmetric, more complex than the models that guided the Voyager missions were designed to predict. This is partly because we had never actually been to the heliopause before to check, which is a reminder that our models of solar wind dynamics were calibrated against conditions far from where they were most severely tested. But the deeper issue is what this tells us about the structure of the local interstellar medium and our place within it. The Sun is embedded in a region called the local bubble, a cavity in the interstellar medium carved out by a series of supernova explosions over the past 15 million years or so. This cavity has shaped the interstellar medium around us in ways we are still mapping. Recent data from the ESA Gaia satellite and from X-ray observatories have revealed that the local bubble's shell is still expanding, still driving star formation at its edges and that the solar system sits very near the bubble's center, which is either a remarkable coincidence or an indication that the bubble itself influenced the conditions of the local interstellar environment in ways that matter for the solar system's history. The exact nature of that influence, the details of how the interstellar medium has varied in the past few million years as the solar system moved through different environments, and what effect that had on climate, on the flux of cosmic rays reaching Earth, possibly on the pace of evolutionary change. These are not settled questions. Now, here is where it gets strange in a way that I have never fully gotten comfortable with, and I have been thinking about it for a long time. In 2017, the first interstellar object detected passing through our solar system arrived. We named it Oumuamua. It was discovered by Robert Warwick using the Pan-STARRS telescope in Hawaii, and when its orbit was computed, the conclusion was unambiguous. It came from outside the solar system, traveling on a hyperbolic trajectory, and it was moving faster than the sun's escape velocity, even at its perihelion. This was the first time we had ever directly observed an object that originated around another star, and it was extraordinary for that reason alone. Then the anomalies started. First, the shape. Based on its brightness variations as it tumbled, Oumuamua appeared to be highly elongated, perhaps 10 to 1 in aspect ratio, a needle or a pancake, unlike anything we had ever seen in the solar system. Second, the composition. There was no coma, no outgassing, no cometary activity, even though it passed within the orbit of Mercury, where solar heating should have been intense enough to sublimate volatiles if it had any. Third, and this is the one that generated the most controversy, Oumuamua was accelerating, not decelerating. As it moved away from the sun, it was speeding up in a way that could not be explained by gravitational forces from the sun or any planet. The residual acceleration required a non-gravitational force. For a comet, this is not surprising. Outgassing acts as a thruster, but there was no outgassing. And the acceleration was not consistent with the radiation pressure a normal rocky body would experience, because the force needed was too large relative to any reasonable mass estimate for an object that size. Unless the object was extraordinarily light for its volume, which is to say, unless it was extremely thin, a very thin slab, or had an extremely low bulk density. Avi Loeb at Harvard published a paper arguing that Oumuamua was consistent with being an artificial light sail, a thin, flat structure constructed for interstellar travel. This generated an enormous amount of controversy, some of it scientific and some of it purely sociological, and the sociological response was not always flattering to scientists. The paper did not claim Oumuamua was definitely artificial. It argued that the artificial hypothesis was not ruled out by the data, that it was in fact consistent with the data, and that it deserved to be considered alongside natural explanations. The response from much of the community was to treat this as an embarrassment rather than a serious argument to be engaged. That is not how science is supposed to work. The natural explanations that have been proposed include a fragment of a nitrogen ice body, which would explain the low density but requires a type of object we have never seen in the solar system before. Hydrogen ice, which faces problems with thermal stability. A fractal aggregate of dust particles held together by electromagnetic forces. And a fragment ejected from a planetary system in some kind of energetic event. All of these hypotheses have problems. None of them is fully satisfactory. The honest position is that we do not know what Oumuamua was. We cannot go back and measure it. It has left the solar system, and we missed the opportunity for a close-up look because we did not discover it until it was already departing. A second interstellar object, Borisov, was detected in 2019. It did have a coma. It behaved much more like a comet. So interstellar space is not exclusively populated by pancake-shaped accelerating needles, which is mildly reassuring. But Oumuamua remains what it was: anomalous, unresolved, and worth taking seriously. I want to talk about something that sits at the intersection of all of these anomalies and points toward what I think is the deepest open question in physics. One that is directly relevant to what NASA sees in its data and cannot explain. It is the question of dark energy. In 1998, Two independent teams, Saul Perlmutter's Supernova Cosmology Project and Brian Schmidt and Adam Rees's High-Z Supernova Search Team, announced that the expansion of the universe was not slowing down as everyone had assumed. It was speeding up. The universe is accelerating. Something was pushing space apart, overcoming gravity on the largest scales, driving galaxies apart from each other at an ever-increasing rate. This earned Perlmutter, Schmidt, and Rees the Nobel Prize in 2011. The name given to this unknown driving force was dark energy. Here is what we know about dark energy. It comprises roughly 68% of the energy content of the observable universe. It is apparently nearly uniform throughout space. It is apparently nearly constant over time, though the Hubble tension I told you about suggests it might not be constant, which would change everything. And we have no idea, none whatsoever, what it is. The leading theoretical candidate, the cosmological constant, which Einstein originally introduced and then called his greatest blunder, and which turned out not to be a blunder but possibly the most important term in his equations, corresponds to an energy density of empty space. Quantum field theory predicts what the vacuum energy density should be, and the answer it gives is approximately 10 to the 120 power larger than what we actually observe. This is the largest discrepancy between a theoretical prediction and an observation in the history of science. By an enormous margin, we are wrong about the vacuum energy by 120 orders of magnitude. Something cancels it almost perfectly, reducing it to the small non-zero value we observe, and we do not know what that something is or why it cancels so precisely without being zero. This is not a problem at the edge of physics. This is a problem at the center of physics. Every quantum field theory we write down, every attempt to unify quantum mechanics with general relativity, has to somehow deal with the fact that empty space is not empty, that the quantum fluctuations that fill it contribute an energy that should be enormous, and that the value we actually measure is smaller by a factor of 10 to the 120th. This is called the cosmological constant problem, and it is 60 years old, and it is unsolved. When I say we do not understand dark energy, I do not mean we are missing a detail. I mean we are missing something fundamental about the nature of space, vacuum, and quantum mechanics. When people tell you physics is nearly complete, ask them about the cosmological constant problem and watch what happens. I have spent years arguing with colleagues about whether the mystery is in the physics or in the mathematics. I have been through periods where I thought anthropic arguments, the idea that only certain values of the cosmological constant permit the formation of galaxies and therefore observers, were the most promising avenue. I now think those arguments, while not wrong, are not sufficient. They tell you which universe you can find yourself in, but they do not explain the mechanism by which the cancellation occurs. And mechanism is what physics is for. Let me bring this back to ground. NASA's missions run into these problems not as abstract philosophy, but as concrete measurement problems. The James Webb Space Telescope is contributing new data to the Hubble tension. The data are making the tension sharper. The Nancy Grace Roman Space Telescope, when it launches, will measure dark energy's equation of state with unprecedented precision and may tell us whether it is constant or varying, which might be the most important measurement of the next 20 years. Instruments designed to detect the polarization signature of primordial gravitational waves in the cosmic microwave background will test theories of inflation that are connected to the cosmological constant problem. These are active scientific programs producing active scientific confusion, and the confusion is productive. But here is what I want to leave you with. Not comfort, not reassurance that the smart people are on it. Something harder than that. We are at a moment in the history of science where the anomalies are not at the fringes. They are not in esoteric corners of physics that touch nothing else. The Hubble tension is a crack in the standard model of cosmology. The ultra-high energy cosmic rays are a mystery about the most extreme processes in the observable universe. The flyby anomaly, if real, is a crack in orbital mechanics. Oumuamua was either the most unusual natural object ever detected or something we do not have a category for. The Fermi paradox is a silence that could mean anything from we are alone to we are the last ones left. Dark energy is a 68% contribution to the universe that is entirely without physical explanation. And the wow signal was a 72-second event that no one has explained. Every one of these is an invitation. They are the universe's way of telling you that the map is not the territory, that the models are not the reality, that the most important discoveries are not confirmations of what we already believe, but failures of what we already believe. Science advances not when theories succeed, but when they fail in ways that are specific enough to point somewhere new. I have watched colleagues become comfortable. I have watched funding agencies become comfortable. I have watched the culture of big science drift toward confirmation, toward incremental refinement, toward the verification of predictions rather than the hunting of anomalies. That is the wrong priority. The anomalies are where the future lives. The things that don't fit, the things that require the footnote and the asterisk and the pending further investigation, those are the most scientifically valuable things we have. Not because mystery is beautiful, though it is, but because every single time in the history of physics that an anomaly has been taken seriously rather than swept under the rug, it has led somewhere we never expected to go. The anomalous orbit of Mercury led to general relativity. The anomalous spectrum of blackbody radiation led to quantum mechanics. The anomalous brightness of distant supernovae led to dark energy, and the Nobel Prize. I am not telling you the universe is unknowable. It is not. It is relentlessly knowable, but it insists on being known on its own terms, not ours. It will not shorten itself to fit the theories we find convenient. It will not silence the wow signal just because we can't explain it. It will not slow down its expansion to match our preferred cosmological model. It will not tell Oumuamua to have a coma so we can feel comfortable classifying it as a comet. It will keep doing what it does, and either we pay attention to all of it, including the parts that embarrass us, or we will keep confusing our map for the territory and wondering why the territory keeps surprising us. Go home tonight and think about this. 68% of the universe is something we cannot identify, that exerts a force we cannot explain, that is predicted by our best theory to be wrong by 120 orders of magnitude. 95% of the universe, dark matter plus dark energy, is made of stuff we have never directly detected, never characterized in a laboratory, never sampled. We are made of the remaining 5%. We are the minority constituent of a universe that is mostly something else. And we have the extraordinary arrogance to believe that because we understand the 5% reasonably well, we are close to understanding the whole thing. We are not close. We are at the beginning. The mysteries NASA cannot explain are not failures of NASA. They are frontiers. And frontiers are not problems to be apologized for. They are the only reason any of this is worth doing.